sound property in range, how sound behaves, and how music helps us visualize its limits. The unheard facts. Part of sound that we fail to interpret can be actually utilized for our benefit. Studies claim that sound does not move at a constant speed. Find out how sounds move and what influences the way they move on our special feature. Statistics show that the majority of the population has a hard time believing that the speed of sound can be calculated. Tune in later to learn how to give this concept a number.
Good evening, physics world. For our first piece of news tonight, we jump to what sound waves are and what range it operates on. As we all know, sound is a mechanical wave and therefore requires a medium to propagate. It is measured by its amplitude and frequency as a way to quantify its properties. But that's not all there is to it. Here's our field reporter, Mr. Danny Arno, to further expound on this topic. Danny?
Sa'yo ko? Okay naman na, ano? Okay. Thank you, Mr. Calbunoy. As we've learned from the first segment, we know that any kind of wave, especially in sound, is measured in amplitude or frequency. Then, I introduce everyone from the property of sound, frequency!
The keyword of frequency, which is frequent, is occurring or done on many occasions, in many cases, or in quick succession. And in sound, frequency means number of times a sound waves repeats itself per second. It stays close to its true meaning.
So now that we've learned its true meaning, we will go on way deeper on spectrum of sound frequency.
Sound spectrum, as a definition, is the amount of vibration found at each frequency, which I have explained, normally depicted using a graph or a pressure as a function of frequency.
But how do we measure this?
Oh, it hurts!
It's the standard unit for frequency. It also represents the number of cycles per second. In layman's terms, hertz is also the term or measure for the sound's pitch.
Quiet down!
To lower one sound, one needs to lower decibels they produce. Decibels is the standard unit of sound pressure or its power. The higher the decibel equals, the louder it sounds.
And since we are talking about sounds, let's talk about the fancier expression of sound, music. In music, we all know there are bass, percussion, and etc. They do this to mix the sound into music.
So, in the spectrum, we have the lows containing sub-bass and mid-bass. Then, there are the mids, which we have low mid, center mid, and high mid. Then the high, having the presence and brilliance. Now that I've held you long enough, since I've been talking too much now, it's time to bring you back to Mr. Calbunoy. Kyle?
Thanks for the enjoyable lesson, Danny. To continue, it seems we have word that there are types of sounds that are deemed inaudible. What an interesting thought. Here's Mr. Kyle Bunoy to back us up on that. Kyle? Sorry about that. It seems Mr. Bunoy is having audio problems. But we may be able to decipher what he was saying. Here it is. It seems there are sounds that are unable to be detected by human ears, earning them the term non-audible sounds. There are two types of sounds that fall outside the human hearing spectrum, which are infrasonic and ultrasonic sounds. Okay, I see. Okay. So infrasonic sounds are sounds that fall below 20 hertz and are commonly used in long-distance communications due to their lengthened wavelengths. Okay, I see. It's also used by elephants in forms of Low frequency grunts to communicate with their herd. The other type of inaudible sound is ultrasound, which are sounds that with frequency of above 20 kilohertz, they are commonly used in medicine for detecting conditions and I see, guiding its treatment. Okay. Dogs, yes, also normally seem to hear this threshold of sound, and therefore why dog whistles exist. It seems that we cannot reconnect, but that was a good shot, Kyle. We again apologize for the inconvenience. Moving on, scientists tells us that the sound we hear doesn't always come to our ears at the same speed, and a lot of factors may matter. We have Mr. Leonard O. Natividad on the scene for this feature. Leonard?
Thank you, Mr. Kyle. I'm here now live at the testing center where engineers test different vehicles at incredible speed because speed is everything in their world. So let's rev up the facts.
The speed of sound is defined as the distance through which a sound wave's point travels per unit of time. However, the speed of sound isn't a fixed number. It changes depending on what it's moving through and how it moves. Let's break it down.
Warmer air is equal to faster sound. That's because molecules move quicker and pass vibration more efficient. In cold weather, sound slows down. That's why thunder seems delayed on chilly night.
Additionally, if you increase a material's density, meaning the particles are heavier, sound can actually slow down. Heavier particles resist motion more. That's why helium changes your voice. It's lighter than air. But remember, density alone isn't everything. This one's crucial. Elasticity is how easily material returns to its original shape after being disturbed. More elasticity equals faster sound. That's why even dense metal like steel can transmit sound faster than air. They snap back quickly when vibrated. Alright, now let's talk about categories of speed of sound. Engineers and pilots don't just talk about speed in kilometers per hour. They use Mach numbers. Named after physicist Ernst Mach. Here's the breakdown. First is the subsonic with Mach less than 1. In this stage, the aircraft is slower than the speed of sound. But if we speed up the next stage, we will be reaching is transonic with Mach under 0.8 to 1.2. It refers to flight speeds where the airflow around an aircraft is both subsonic and supersonic at the same time. But fasten your seatbelt because we're reaching to the supersonic. Supersonic with Mach number 1 to 5, it is 4 times faster than speed of sound. When an object travels at supersonic speeds, then it is the time where it is entering the sonic boom territory due to creation of shock waves. Shocking, isn't it? Lastly, the hypersonic, with a Mach number greater than 5. It is so fast that air begins to dissociate and ionize.
So you see, speed of sound isn't just about moving faster. It's about how nature's moving through matter. Stay curious, stay loud, and keep learning. I am Leonard Natividad, and this is your P69 Tonight Science Report. Back to you, Kyle.
Beautifully put and well done, Leonard. For our final story of the night, research shows that a lot of people find it hard to believe that the speed of sound can be calculated just like that. Immediately following the topic of factors affecting the speed of sound, it seems we have Miss Ivrem Catriel M. Fernandez to teach us how to actually calculate the speed of sound through different media. Without further ado, Miss Ivrem.
Yes, Mr. Kyle Christian Gabriel Bunoy. Again, good evening. We are here on the scene of the speed of sound. As of now, new calculations are to be learned. We have the three types of medium, solid, liquid, and gas, to provide us the new formulas we will use along the way to calculate and solve for the speed of sound. Many people believe that the solid medium helps the speed of sound to travel faster, such as the material commonly used in construction, the solid concrete. The density of the solid concrete is 2,800 kilograms per cubic meter, and its elastic modulus amounts to 2.5 times 10 raised to 10 pascals. We can calculate for the speed of sound in solids through the formula V is equals to the square root of E, Young's modulus, also known as modulus for elasticity, over the density of the solid. For our given, Young's modulus is equals to 2.5 times 10 raised to 10 pascals. And the density of the solid is equals to 2,800 kilograms over cubic meters. For our solution, we take our formula and substitute our values. Thus, we have the square root of 2.5 times 10 raised to 10 pascals over 2,800 kilograms per cubic meter. And the speed of sound, V, is approximately equal to 2,988.07 meters per second. On our next type of medium is the liquid. And what other liquid is there as more as common as water? Let us see how water accommodates the travel of the speed of sound. The density of water is 1,000 kilograms per cubic meter with a bulk modulus of 2.2 times 10 raised to 9 pascals. The formula for the speed of sound in liquid is V is equals to the square root of B, which is bulk modulus of the liquid, also known as resistance to compression, over the density of the liquid. For our given, we have the bulk modulus equals to 2.2 times 10 raised to 9 pascals, and our density is equals to 1,000 kilograms per cubic meter. For our solution, we take our formula and substitute our values. Thus, we have the square root of 2.2 times 10 raised to 9 pascals over 1,000 kilograms per cubic meter. Thus, the speed of sound through liquid is approximately equal to 1,483.24 meters per second. Last but not least is the gas. There are many kinds of gas, but the spotlight goes to the one around us, air. And there are a few more factors to consider when calculating the speed of sound through air. The summer day emits a temperature of 35 degrees Celsius. The molar mass of dry air is 28.96 grams per mole, and the adiabatic index air is approximately 1.4. In some cases, when the pressure of the gas is present, we can use the formula V is equals to the square root of gamma times pressure over density. But for now, the formula to be used is V is equals to the square root of gamma multiplied to R, the universal gas constant, times the absolute temperature in Kelvin over the molar mass of the gas. For our given, we have the gamma, which is the adiabatic index equals to 1.4, R is equals to 8.31 joules per mole Kelvin, T is equals to 35 degrees Celsius. Converting it into Kelvin, we add 273, which is equals to 308 kelvins. M, the molar mass of the gas, is equals to 28.96 grams per mole. Converting it into kilograms per mole, we divide it by 1,000, which is equals to 0.02896 kilograms per mole. For our solution, we take our formula and we substitute our values. Thus, we have the square root of 1.4 times 8.31 times 308 over 0.02896. Thus, our speed of sound through air is approximately equal to 351.76 meters per second. Now, we have calculated for the speed of sound in solid, liquid, and gas. This is your reporter, Ibrahim Fernandez, on P69 tonight. Back to you, Mr. Kyle Christian Gabriel Bunoy.
That was very informative and easy to follow. Thanks, Miss Ivory. May this educate the public better on how to use mathematics and physics in our daily lives. Well, it seems as that's all we got for you this fine evening. I hope this evening had been very informative for the new and experienced alike. I'm your host, Kyle Christian G. Bunoy. Meet us back here, same time, same channel tomorrow. Listening everything, even time zones, but not the truth. This is P69 tonight.